Hello everyone, welcome to this video. My name is Emerson Ahrari. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to do MODIS NDVI sharpening in the Google Earth Engine platform. In this tutorial, we aim to use machine learning technique and Landsat images to see that or to show that how we can improve NDVI product from 500-meter spatial resolution to 30-meter spatial resolution with daily temporal frequencies. And also this is very useful tutorial in the Google Earth Engine Expert that enables you to use machine learning techniques to improve the quality of data you are using. So let's go to the Earth Engine Code Editor environment. Here, first of all, draw your region of interest through the drawing tools available here. We need to find a region and then call Landsat and MODIS NDVI product for that. So here, for example, I'm gonna select farmlands in the southwest of Iran. As you can see here, lots of croplands available here. You can use this tutorial for all around the world. And also, but one thing is important, your study area should be included vegetation cover, whether it is forest or croplands or rangeland. So, throw a rectangle. I'm gonna make a region here and I draw it using rectangle tools available here. So, then if you need to make any change, here pan or pan or a hand sign can help you to select the region of interest and make a change in the dimension and location and etc. So in the next step, to have focus on the study area, use map.center object, helping you to focus on the geometry or the region of interest we selected. Then make a new variable for Landsat images. We have a variable as Landsat. Through the search places on dataset, find Landsat collection 2 level 2. Landsat collection 2. It would be better to use Landsat 8 because Landsat 8 data are regularly available for the users. And also we have no noticeable gaps in the Landsat 8 from Landsat 8 on. So here, Landsat 8, collection 2, level 2 product. Level 2 product imported into the code. We have it as an image collection. Here, we have it as an image collection, and then we need to set the filters, boundary filters, and also the date filter. That filter bound allowing us to call Landsat images that are covering the selected region. So filter bounds according to the region. I need to those Landsat images that has intersect with the geometry I have drawn. Then through that filter dates, we can call Landsat images for a specific period of time that we are studying. For example, my target period of time is starting from 2020 to 2021. Accordingly, make two new variables for the time start and time end. Time start is 2020 and time end equals to 2021, meaning that we are calling all Landsat 8 collection 2 level 2 for the region of interest that has taken by the satellite or Landsat data in 2020 from January to December. Here, filter dates including time start and time end. Through the print function, you can see how many Landsat data available in this period of time. And also you need to remember that some Landsat images has framing structure, and maybe your region of interest covering by various paths and rows or various Landsat frames. In that step, we need to select one frame or those of frames that completely covering our study area without any gaps. So here, as you can see, 41 element data are available. If you go to the elements or the features, you can see that all images related to each image related to a single date, and also the metadata information completely available and helping us to get some information about each product and each frame. As you can see, the target paths and rows helping us to understand what paths and what rows actually covering the region of interest or has intersect with the region of interest. It's very simple technique that aggregate helping us to understand how many paths and rows or how many frames actually covering this area. Target WRS paths. Here I need to know how many WRS paths we have, target WRS paths or WRS paths or WRS row, no difference. So I need to know how many paths are related to this area. Through the dot distinct, I'm able to see the unique values for the paths and also without duplicating same values. So you can use the same code for the rows, WRS rows, and then run the code. As you can see, row S was extra. As you can see, the main path for the data covering this region is 166, but we have two rows, meaning that two different frames covering this region, and I need to know which one fully covered my area. To answer this question, you can use Earth Explorer website. As you know, the Earth Explorer powered by NASA and USGS, and this is the main hub releasing Landsat images or Landsat missions for over the last years. So here, as you can see, we have a map. No need to do registration in this website anymore. Just I want to show you how you can find or how you can know which path and which row covering your study area. It's very simple. Here we have a Google map, and now you can find your study area easily. For example, my study area is located in the southwest of Iran. Select the region of interest and no need to set anything, just go to the dataset. In the dataset, the Landsat tab, open it up and then collection to level 1 or collection to level 2. No difference for the paths and rows. Landsat 8 and 9 selected, go to the result and waiting to the result. Once the result available, as you can see, one path is 166 and the row is 37. This frame covering a part of our region of interest, while the second one, 166 and 38, as you can see, fully covering our study area. And here you can see that this frame, 166, 38, fully covering our study area, and we can use this for our process, because when I want to make a regression analysis between Landsat and MODIS, it is very important to have a data without gap, without noise, that fully covered my region of interest. Back to the code, and we got it. 166 and 38 are the main pass and rows for the further processing. So accordingly, make a new filter for pass and row. Earth engine.filter dot equal filter, helping me to find those of images in which the WRS pass is equal to 166, and then another equal function or equal filter allowing to find those of images in which WRS row is equal to 38. So get rid of previous code and then print Landsat variable. As you can see, only 21 images with 16 days interval are available according to the pass and rows we selected. So in the next step, I need to call those of, or I need to filter those of Landsat images that are which have less cloud cover compared to the others. It's very important things, because when you want to make a regression analysis between two types of products, any noises, including satellite or cloud cover, will have negative impact in your equation, and also it will have negative impact too in the predictions part. That's why very important to use cloud-free images for the regression analysis. In this case, you can have a actually accurate prediction for the sharpening process. So now we can make a new filter according to the cloud cover. If you go to the data description, in the properties, you can see that here there is a property as cloud cover that helping us to find those of images that are cloud free and also without cloud noises. Here, make a new filter, filter again, Earth engine filter less than. As I need to use cloud free images, now I need to call those of Landsat data in which cloud cover is less than 10%. So cloud cover less than 10%. You can also, if there are no, if you don't have access to enough cloud-free images in your study area, you can increase the temporal extent in a larger period of time. Definitely, you will have access to more cloud-free images, and then you can make a more accurate and more reliable estimation equation for the prediction in regression parts. So then run the code. As you can see, 17 elements for 1 year available for this region in which cloud cover is less than 10% in the whole of the frame. In the next step, I need to calculate the NDVI for all of these images. To do this, we need to make a loop, and then using NDVI function, we will be able to calculate NDVI for each element separately. That map is a popular function that working as a loop here. Map, make a new function inside each input image named as an IMG, and also in the function body you can write your target equation. For example, first of all, I need to calculate the surface reflectance values. If you go to the data description, here you can see the basic description about the data and dataset availability. In the bands, in addition to the spatial resolution, the bands or multispectral bands are available. In the new page, you can see better with more details. Under the tab, under the bands, you will see that we have a scale and offset values that are available in the image metadata, and you must use this to convert the multispectral band from the integer range of value or digital number values to the surface reflectance values. It is mandatory process when you are working with Landsat data, specifically for spectral indices. Back to the code and go to the data description. Go to the data properties, sorry. In the data properties, as you can see, the scales and factor available with the same value for the multispectral band. We can use these values for the calculation from digital number to the surface reflectance value. For example, one of the coefficients, we have two constants. One of them is add and one of them is molt. There is a linear equation between digital number and surface reflectance in this product. And here we have gain and offset for each band with the same values. Now I can extract or get these values from the metadata and apply them on each multispectral band. Make a new variable as gain equals to from each input image dot get. Whenever you want to extract some information from the image properties, you must use get. Dot get, for example, I need to get a gain value or multiplicative value. So here, like this, one of the bands selected, and then we need to convert it as a number. Another one is offset equals to EarthEngine.number from each input image, extract or get reflectance add band. So no difference which band you are using, because we have the same value for additive, for addition, and also multiplication. Now another variable is multispectral bands equals to from each input image. First we need to select surface reflectance bands. Here I can select all available surface reflectance bands and then apply the gain and offset value through the linear equation. Surface reflectance bands multiply the gain value that add to the offset value. So then we can use the multispectral image that is including surface reflectance values for the NDVI calculation. Here we have NDVI equals to from multispectral bands dot normalized difference. Calculate the normalized relationship between band number 5 and band number 4, surface reflectance band 5 and surface reflectance band 4. Then name it as Landsat. That will be Landsat NDVI. So finally, the function returning the NDVI as the main output with the time information for or the date acquisition for each image through the dot copy properties, img and img property names. So code is ready, or the NDVI is ready for the Landsat data. Save your code and run it again. Here we have 17 elements. Sorry, here I made a mistake. In order to copy the date acquisition information to the NDVI images, we need to have system time start and system time end. It was my mistake. Time end. Run the code again. So here we have 17 elements or 17 images. In each date, we have one NDVI calculated based on Landsat images with 30-meter spatial resolution. And also the system time start properties also available that helping us to do the time series analysis in the next step. After Landsat NDVIs gets ready, in the next part we need to call the MODIS daily NDVI images. That is also a very important part. If you want to use or call the Landsat MODIS NDVI product into the Google Earth Engine platform, there is a simple way that you can type it in the browser, Google Earth Engine MODIS NDVI daily. Just type it, and in the Google search you can find MODIS Terra Daily NDVI. This is the fastest way to find this product in the Google Earth Engine platform. Through the data catalog, finding this product is a little tricky, but the simplest way is to type its name and Google Earth Engine on the web to find it properly. So the image is available. This is the NDVI, daily NDVI, available since 2000 and also with 500-meter spatial resolution. As it is already calculated, it doesn't need to do the calculation or any new calculation anymore. So the only thing you should do is to copy the collection snippet and paste it into the code editor. So let me to make a bigger space for codes. Now make a new variable as MODIS equals to paste the collection snippet for the MODIS data, and then define the filter date for the MODIS NDVI product from time start to time end. So here, as you can see, the MODIS NDVI data available for the same period of time that we have Landsat images, and its NDVI is already calculated, and we don't need to do the calculation anymore for the MODIS NDVI. So here print MODIS data to see that how many MODIS products or NDVI available. In this year we have 366 NDVI values or NDVI images for in the MODIS product with 500-meter spatial resolution. One side there is Landsat NDVI, 17 Landsat NDVI for 1 year, and the another side 366 NDVI in the MODIS side. So now we need to join these two products in the consistent dates. So the main task here is to find those of MODIS images that is equal, that consistent with the Landsat data from the date and time point of view. It's very important to find the same dates, Landsat and MODIS NDVIs. We can do this process through the join function into the Google Earth Engine platform. And as the MODIS data, because of daily temporal resolution, highly suffering from cloud cover, we need to make a maximum, we need to do a maximum value composite in MODIS images. For example, the strategy I want to use is that find all MODIS images within 3 days of each Landsat data, and then get their maximum value to produce a cloud-free MODIS images and then use this product for the regression modeling. So in the first step, I'm gonna show you how we can find MODIS images within 3 days for each Landsat image. In the first step, it sounds a little complicated, but using the join functions and maximum difference filter, it's very easy process, and you don't need to do complex programming technique. Just with combination of some simple functions, you can do this process easily and without any complexity. In the first step, we need to identify the number of the days within we need to call MODIS data for each date that Landsat is available. As I'm going to call, for example, MODIS images within 3 days of Landsat data, the days number here could be 3. Then I need to convert the days from this format to the millisecond format. Here I have a millisecond variable EarthEngine.number taking the days and then multiply it to this equation 1000 multiply 3600 multiply 24. This equation converting the days from this unit to the millisecond format. So as you can see, this is the millisecond format for the number of the days. If you followed my previous tutorials in my YouTube channel, certainly you know that I always point out Google Earth Engine using the millisecond format for the time series analysis. That's very important to convert or interpret or translate the times from the current unit or from the normal unit or normal format to the millisecond format. So back to the code. Now we need to make a maximum filter date. The maximum filter date is going to help us to find corresponding MODIS images compared to the Landsat data within the 3 days difference. So make a new variable as filter EarthEngine.filter max difference. The max difference helping us to do this process. The difference in this filter is the number of the days based on the millisecond format, and the left field and the right field. Here we have 2 image collection. One of them is Landsat and another one is MODIS. And the field in which we want to find correspond Landsat and MODIS data is the system time start for the left image and right image. The left field equals to system time start and the right field is also system time start. The value should be null. No need to have any value for this. So as you can see, the maximum difference is a sort of filter, is a sort of temporal filter that's helping us to find the corresponds images within the 3 days difference. That's how this filter works. Next, after making the maximum difference filter, that is a kind of temporal filter, we need to make a join function. Here the join equals to EarthEngine.join. There are different methods for the joining process. One of them is save all, meaning that find all images all corresponding images for the days before, for the days after in the corresponding dates, and also to save them into a match key. You can set any name for the match key. For example, here the match key here is MODIS, because I need to find the MODIS images within 3 days of Landsat data. The ordering doesn't matter, and ascending, descending, and measure key and outer, none of them are important. Remove all of them. So, and then we can combine the filter and join together. Make a new variable, join data equals to Earth engine dot image collection. Get join function and apply it on 2 image collection. The first image collection, or the primary, is Landsat, and the second image collection is MODIS data. So join MODIS to Landsat based on one condition. The condition here is filter or maximum difference. Find join Landsat and MODIS according to the 3 days difference, meaning that for corresponding dates we have Landsat and MODIS. Find MODIS images until 3 days after and before Landsat dates, because we want to get a maximum value from these images to produce a MODIS clot-free product to get a good relationship. Now print join data to see what's happened after code running. Run the code, image collection under computing. Again, we have 17 elements. If you go to each feature in the properties, you will see that one new property added. The new property named as MODIS. As you can see, in the match key, we made a new properties as a match key named as MODIS. And now you can see that for each Landsat image, there is a new property in which including MODIS NDVI within 3 days after and before each Landsat NDVI. For example, here you can see that for this Landsat image, actually all of the bands and also all of the MODIS NDVIs within the 3 days are available. The Landsat image here is related to March 25. And as you can see, the March 25, 26, 24, 27, 23, and 28. After and before that date, within the 3 days, gather it together. And now I can get a maximum value from these images to make actually the clot-free image and add it as a new band next to the Landsat NDVI data we have. That's what we did so far. So now in the next part, I'm gonna show you how to get maximum value for the images under the MODIS property and adding as a new band into the main image collection. It's very simple. So now again, make a new variable as collection. Here I'm gonna make the final collection. For each date I will have Landsat NDVI and the MODIS NDVI. So here I have join data and then throw the map, make a new loop. In the loop we will have a function that's named input images as an img, and here in the body now make a variable as, for example, this variable is images equals to from input image dot get. Go to the properties and get images under MODIS property dot get is a function helping us to get information that are available in the properties. So now I want to convert it from actually a property to an image collection that allows me to calculate the maximum of all images under the MODIS property. Earth engine dot image collection from images. From all images available in the MODIS, I'm gonna make a collection like this and then get the maximum value for the data available within the 3 days for each corresponding date. So that's what it looks like. And then the maximum is a function that calculates the maximum value of each pixel, and also as the cloud cover reduce the NDVI values, the maximum value composite can reduce the cloud impact as much as possible. So this is one of the most famous and popular methods for the NDVI temporal collections. Finally, this function is going to return the maximum MODIS NDVI image next to the Landsat. The function returning input img that add bands with the images with the maximum image calculated from images variable. Through the rename, you can turn its name from max to the MODIS variable. And no need to copy the properties because it is already included. So now I'm making a new collection and printing to see what's happened. Again, 17 elements are available, but this time for each date, 2 bands available. 2 NDVI, one of them related to Landsat and the other one related to MODIS. As you can see, it is available, and now for the next step, we can make a linear regression model between Landsat and MODIS images to make a prediction model that's used to predict MODIS high-resolution images. So for the next part, we need to make a model, the machine learning model, that is regression. Actually, the linear regression is one of the techniques, one of the popular machine learning techniques that highly used in the remote sensing and geographic information system. This is one of the popular statistical methods that people usually use for different applications and widely applicable in the remote sensing and GIS. So here we have a model. In the model, Earth engine, no need to add some Earth engine image collection. Just call the collection first and then throw a map, make a new function to add dependent and independent variable. So in order to calculate the linear regression model, we need to have one constant band next to the dependent and independent variable to get a realistic output from the model. So here, make a new variable as constant Earth engine.image.constant. The image including value number 1 as a constant band, and then the function returning independent bands and the dependent bands. Independent bands comes first, then we will have the dependent bands. So the independent is first img.select MODIS, and then .add bands. We have the constant value, and then we will have the dependent variable. The dependent variable is Landsat. We need to know how Landsat changes compared to the MODIS data. And then after selecting the dependent and independent data through the reduce, you can calculate Earth engine.reducer.linear regression model. Linear regression, there are two arguments for x, independent variables, MODIS and constant, and y, dependent variable, is Landsat, only one variable or one dimension. So print to see model in what we have in the model variable. Run the code again. We will have one new image, but there is a problem here. So meaning that need 3 bands for the reduce.linear regression, but image collection has 3. So here we have constant through the add bands. Oh yes, the problem is here we need to have add bands here instead of add. Run the code again. Here we have one image with 2 bands. One of them is coefficient and one of them is residual. The coefficient has 2 dimensions. One dimension refers to gain, and also another dimension related to the offset. The gain showing the slope of changes between dependent and independent variables. So here we need to have or extract the gain and offset from the coefficients. The gain for model equals to from model.select. First select coefficients and then through array get, it has array structure with 2 dimensions. The first dimension including gain image and the offset equals to from model first select coefficients dot array get the second dimension will be offset. So the main parameters for the prediction model are gain and offset that is created and extracted from the cloud-free images in the corresponding date between Landsat and MODIS NDVI. Now what you need to do is applying these coefficients on the MODIS images, on MODIS daily data to get higher spatial resolution. Actually, using this model or equation, we want to inject the spatial detail into MODIS images. So to do this, make a new variable MODIS 30 meter equals to, so now we need to call original MODIS data with the daily temporal resolution and then throw .map, make a new function to apply the linear regression model on each existing MODIS NDVI. Each input image named as an IMG, and now make a prediction model equals to each input NDVI as IMG dot multiplied gain and added to offset. So this is the prediction model to reach to the MODIS NDVI with 30 meter spatial resolution. So finally rename it to NDVI 30 and function returning NDVI with 500 meter as an IMG, and then we will have the prediction or NDVI with 30 meter spatial resolution. Through the dot copy properties, you will have the properties of inputs for the outputs. So print MODIS 30 and runs the code. As you can see, a new collection with 366 elements returns. For each date, 2 NDVIs available, one of them with 30 meter and one of them with 500 meter spatial resolution. I can rename it to see better. This is NDVI 500. Run the code again. A new collection. Features, 2 bands, one NDVI 500 meter and one 30 meter. Now I want to do validation to see that is it possible to have 30 meter spatial resolution in the MODIS NDVI data, and also we want to know that the scenario was correct or not. We had some difficulties or we have some challenges in the output. The best way for the validation is the visual comparison to see that how much NDVI changes and also how much spatial detail improved. You can do this for the visual visualization through the map.add layer. So the MODIS 30 is the final result, .2 bands, making a stack layer, and then clip it based on the geometry. Leave the visualization parameters empty, and the layer name is MODI NDVI sharpened NDVI sharpened, and use the false. Avoid automatic visualization that increases the speed of processing. So now code is running, and in the layers we have NDVI sharpening, and then as you can see NDVI 500 meter and 30 meter is available. For example, for one of the dates randomly for May 26, for example, the NDVI 500 meter May 25, this is May 27, but let me to select a time that we have more vegetation cover. For example, July 11. July 11, increase the contrast for the output. This is the original NDVI value we had. Check it on. This is the original NDVI value we calculated for this time. And now you can see 30 meter spatial resolution for this date. So here, this is with more spatial detail, but you can use different methods for the visualization. Sometimes some outlier values reduces reduces the quality of final image. For example, in another date, for example, NDVI with 500 meter August 23. This is for August 23 with 500 meter and with 30 meter. You can see the result. Maybe the contrast a little changed because of the regression technique. For some dates, we have a better visual characteristic, and for some dates, because of the remained cloud cover or some of the noises, definitely we may have some poor quality. And also the quality will be different from one time to another time, because if we have cloud cover in the daily NDVI values that we are applying the equation on, definitely we will have some distortions in the output. That is not a surprising thing for in this kind of calculations. And this is for May 14. I'm increasing the increasing the contrast. As you can see, this is with 500 meter spatial resolution, and May 14 with 30 meter spatial resolution. And you can see that how much the range of NDVI values changing for each date. Then apply the code, and then you will see that, for example, in the last 2 dates I have selected, we had a better quality. And as I said, maybe sometimes cloud cover or some noises in the original NDVI for the daily data cause bad estimations in our study, actually. And you can also increase the contrast of increase the quality of outputs by the smoothing technique that I have already showed you in my tutorials in my YouTube page. And also one more thing is the temporal time series, and we can compare the temporal variations of NDVI with 500 meter and 30 meter to see that how much the NDVI values changed from 500 meter to 30 meter. The main goal is to keep the spectral characteristics same, just improve the details or inject the new details. And if we lost the spectral characteristic and the quality of NDVI reduced, meaning that the amount of actually uncertainty will be a little high in our estimations. But it is important to have a good correlation between NDVI 30 meter and NDVI 500 meter. So, and now through the user interface .chart, user interface .chart image.series, I'm gonna show the MODIS 30 meter changes, including 2 bands already. The arguments listed here, MODIS 30 meter, the region of interest, for example, I'm selecting a new region, for example, this region. Oh, sorry for my mistake, and I mark this region as a point of study. This is geometry number 2, and geometry number 2 and reducer, as it is a marker, we need to get the first value in this point. Earth engine.reducer.first, and the scale should be 30 meter because we improve the spatial resolution, and the X property will be system time start. Now the code is running, and we will have the NDVI variations for the selected point with 30 meter and 500 meter spatial resolution. So as you can see, we have a very good correlation between 500 meter and 30 meter. This is a good sign that showing that we could be success to keep the spectral characteristic, and then we increased the spatial detail. It is true that we have lots of noises in the daily data. This is another subject. If you want to reduce the noises in the daily data, you need to do a smoothing process that it is already actually I showed in my videos. And also if you go to my channel in the YouTube page, I showed you how we can smooth NDVI for the daily data. But what is important here is that visually you can see the increased spatial detail, and also in the temporal changes we could save the spectral characteristic of original data. That is very important in the sharpening technique. I hope you like this tutorial and you can use it in your own project. If you had any question or any problem regarding this, you can reach me out in my YouTube channel, and also I will be check and answer your question as much as possible. Thank you for your attention.